So the title is different from what I had advertised, but it's the same contents. It's just that the title is different. So this is a joint work with Kumar. I'm going to start some introduction here. So suppose M is a mixed motive over a number field K. And I mean, I'm going to stay vague about this. So, any reasonable category of motives, you're working in there. And then via Tanakian formalism, you can associate to M an algebraic group called the motivic Galois group of M. And I'm going to go, over this in more details in a minute. But you can associate a group to this motivic Galois group of M. And then one of the sort of biggest conjectures in arithmetic geometry is Grothendieck's period conjecture, which predicts that the dimension of this group should be equal to the transcendence degree of the field generated over Q by the periods of the motive. So this is very interesting conjectures, because on one side you've got information about periods, and the other side something very geometric. So it's a very interesting conjecture, very deep conjecture. Now, on motives, you of course have a weight filtration. So when I say motive, you can think about it, mixed motives, as cohomology of a general varieties, let's say. And then there's a weight filtration there. So there's associated graded. This is now going to be a direct sum of pure motives. Pure motives like cohomologies of smooth projective varieties. And then this is going to be a semi-simple object. And you will have an exact sequence of algebraic groups. So the motivic Galois group of M is going to surject to the motivic Galois group of the associated graded, which will be a reductive group because that's a semi-simple object. And then the kernel, it's going to be a unipotent group, or the unipotent radical of, and it's the unipotent radical of the motivic Galois group of M. Now, this unipotent radical is related to extensions in the category generated by M. And all of this is going to become more apparent as we go through the talk. And there's a recent result of Deligne, which appears, by a private communication. It appears as an appendix in a 2014 Invention, a paper of Yosen. It's written by him, but it's from a private communication by Deligne. And he gives a description of this unipotent radical in terms of the natural extensions that you would get from M because of its weight filtration. So extensions of the form WpM injecting into M and then quotient map into this thing. And these are the extensions that appear in the title, instead extension classes of M. These are the extensions that I was referring to. So now the plan of the talk is the following. I'm going to go over some background material on Tanakian categories. Then we're going to go over Deligne's result. And then after that, we're going to give a report of on the joint work with Kumar. So let me start with the background portion here. So let's start with a brief reminder on Tanakian categories. So what's a Tanakian category? By that, I mean a neutral Tanakian category. So this, roughly speaking, is a category that has the same properties as the category of representations of a group. So more precisely, so the category is abelian. So this is a Tanakian category over K. Characteristic 0. So T is abelian. It's K-linear. There's a tensor structure. You have internal harms in the category, which is to say that for any two objects M and N, there's a canonical object internal harm of M and N. Defined by universal property, but now, if you were working in a category of representations of a group, this would be just linear maps from M to N, considered as with the natural representation of the group, like basically conjugation. And then, so for any object, you define it dual to be internal harm M, 1. This is the unit object of the category. And then you also require that the double dual, there's a canonical isomorphism between the double dual and the object itself. So I think as I was explaining, maybe I think I didn't use the word finite dimensional. So it shares the same properties as the category of finite dimensional representations of a group, and this comes from there. And then you also require that the endomorphisms of one, the unit object, is the field. And the neutrality, that adjective neutral, means that there's a fiber functor from T to vector spaces over K. Now, what's a fiber functor? It's an exact, faithful K-linear tensor functor. So in the setting of representations of a group, there's natural fiber functor, namely the forgetful functor, right? Setting the representation to its underlying vector space. Now, the fundamental theorem of this theory is the following. So, as I said, I mean, this is basically defined mimicking the properties of category of representations, finite dimensional representations of a group. And the fundamental theorem is that any such category is equivalent to the category of representations, finite dimensional representations of an affine group scheme over K. So, more precisely, we're going to give what precisely the equivalence of categories is. So suppose T is Tanakian and choose a fiber functor omega. And then you define this functor going from K algebras to groups. It associates to a K algebra R the automorphisms of this composite functor. So this is just omega, and then you extend the scalars to go to R modules. So to any, commutative K algebra R, you associate this automorphisms of this functor, omega essentially after extension of scalars, which respect the tensor structures. And then the theorem says that, well, first of all, this functor is the functor of points of an affine group scheme over K. And secondly, so see, the point is that if I take any object in A and any object in T, by definition, omega of M carries a natural representation. So by definition of this guy here, omega of M carries a natural action of that, right? Because these are automorphisms of this functor. So omega of M, points of the group are going to act on omega of M. So for any M, you get a natural representation on omega of M of this group, and the theorem asserts that this is actually an equivalence of categories. And then I'm gonna use this notation that this group I'm gonna denote it by this guy here and call it the fundamental group of T with respect to the fiber functor omega. Now, well, so if you continuing with this background material, suppose you pick an object M of T. Now, by this guy here, I mean the smallest full Tanakian subcategory, which contains M and is closed under taking sub-object. So essentially what you do is that you start with M and the unit object, and then you make it closed under, the sort of obvious operations. So direct sum, tensors, duals, and, sub-objects. And hence subquotients. By duality, you also get subquotients. Now, so this is itself now a Tanakian category, and given a fiber functor omega T, you can restrict omega to this guy, and you're gonna get another group associated to that. And this I'm just going to denote it by GM omega and call it the fundamental group of M with respect to omega. So to link it back to what we discussed in the beginning, the motivic Galois group of a motive. So that comes from this formalism. If you take your T to be the category of mixed motives over K, and as I said, so I'm going to stay vague about this. It's a reasonable category of mixed motives. Nowadays, there's Ayub and Norris categories, which are equivalent to each other. So you can take it to be that. And then omega B. So you got the Betti realization gives you a fiber functor. And then, so now this guy becomes a Tanakian category over Q. And then if you take a mixed motive of M or K, so the group that is associated, the fundamental group of that with respect to the Betti realization is what we earlier, in the beginning, I called the motivic Galois group of them. Okay. So now we're continuing, with the background. Now we're going to sort of give the setting of the rest of the talk. See, in the category of motives, there's a weight filtration. And for what I'm going to talk about, really, you don't really need to work in the category of motives. All you need is that weight filtration. So from this point on, I'm going to assume that T is a Tanaki category over K, field of characteristic 0, and it's equal to the weight filtration. By which I mean a filtration that is similar, satisfies the same similar properties to the weight filtration on motives. So namely, so for any object M, you've got a filtration on M, increasing and finite, and the filtration is functorial, and it's exact, compatible with the tensor structure, and moreover, the associated graded is also exact and faithful. So these are the properties that the weight filtration on motives or the weight filtration on mixed Hodge structures, if you want to think about that category, satisfies. Now, if you take an object M in T, well, so the associated graded of M, well, this will be a subcategory of the category generated by M itself, and by the restriction action to the subcategory, you get a map from the group of M to the fundamental group of the associated graded of M, which will be surjective. And then the U of that, well, by UMW, I mean the kernel of this map. So this would be the elements of this group that act trivially on GER-WM, on the associated graded. It's a unipotent group, and in fact, if GER-WM happens to be semi-simple, which will be, if you're thinking about geometry, categories of motives, blah blah blah, this will be semi-simple. But if that is semi-simple, then this will actually be the unipotent radical of GM. Now, okay, so GM acts on its own Lie algebra, the adjoint representation, and that restricts to an action on the Lie algebra of U, which I'm going to denote by literally. And now by the fundamental theorem of Tanaki categories, see, so the category of representations of this is equivalent to this category. So once you have this representation, there's an object associated to that. So you get an object, which I'm going to denote by underline U, in this category, whose omega is exactly this guy here. And you see that I dropped omega from the notation here. It's because actually this guy doesn't depend on omega. And so, to sort of like think more explicitly about this underlying U, see, by looking, so this elements of this are automorphisms of omega restricted to the category generated by M. In particular, elements of this are going to act on omega of M itself. Right? So you're going to get a map from here to GL of omega M, which is injective because everything in the category generated, if something acts trivially on M, it's going to act trivially on everything generated. So you can think of this group actually as a subgroup of GL of omega M, and then via that, the Lie algebra of that the U group, capital U group that we had, that the algebra becomes a sub-Lie algebra of the Lie algebra of this, which is just endomorphisms of omega. But in fact,
yes. Just to be clear, the reason you can assert that there is an underlying object U bar of M is because it's a module for the group, right? For the fundamental group.
Yeah, exactly. Yeah, it comes from the representation. Absolutely. Yeah.
Okay.
Absolutely. Yeah. Now, see, now elements here, because they're supposed to, they're automorphisms of functors, so they respect morphisms. In particular, they're going to respect the weight filtration. And to be in U, actually, the elements that are in U, they're gonna induce the identity map on the associated gradient by definition. So you see that actually this guy not only, so it's in the Lie algebra of this, but in fact, it's in W-1 of that, by which I mean the endomorphisms of omega M that drop the weight filtration by 1. So more precisely, such that which send omega of Wn to Wn-1 for every n. So, if you take your bases appropriately, so you're writing things in terms of matrices, this would be, upper triangular with ones on the diagonal, or, better than that, So this is going to be contained in the parabolic subgroup associated to the weight filtration, and this is going to be in the unipotent radical, well, the U group, capital U group is going to be in the unipotent radical of that. And so this Lie algebra, well, the Lie algebra is going to be with zeros on the diagonal. So strictly upper triangle. Okay, And then the object that so it's easy to see that, the actions are actually, the action of G here and the action of G here are actually compatible with each other, with this inclusion. So you actually get that this underlying U is a sub-object of W minus 1 of internal harm M comma M, which I'm going to denote by underline end M. So this guy now is a sub-object of this. Okay, so now we're ready to go to Deligne's characterization of underlying UM. Okay, so how does this?
Sorry, just one more thing. So W minus 1 of end M is itself an object, right?
Correct.
Because,
exactly.
Because the action of the fundamental group respects the weight filtration.
Absolutely, yeah, exactly. So I mean, this is an object in the category, and then the category has a weight filtration. So W minus 1 is going to be an object there, and then omega of that is exactly going to be what we defined here.
Yeah.
Okay, so now going over Deligne's characterization. So okay, so M, weight filtration on M for every P gives you an extension like this. So M, gives you an extension of M mod WpM by WpM. So this is gives an element of X of this X group, and then there's a canonical isomorphism. Basically constructions from linear algebra. Give you a canonical isomorphism or representation theory. Give you a canonical isomorphism between this X group and X group. So you can basically take this guy and move it there, replace it with its dual. So X to 1 and then internal harm M mod WP comma WP. And then so there's an element associated to this extension, and I'm going to denote that by script E sub P of M. And I'm going to call it maybe the Pth extension class of M. Now these Pth extension classes live in different spaces, of course, but there's a way to think about them in the same space, namely, by functoriality. If you use functoriality in both variables, you see that there's, you get an injection from this guy to here. See, the point is that if you give me a map, so once I apply fiber functor, I can drop the underlines, and these are just going to be linear algebra things. And then if you give me a linear map from M mod WP to WP, I can just go from M to this guy and then to here and then inject into M again. So I'm going to get an isomorphism of M. And if you think about it, you'll see that the weight filtration is indeed dropping because modding out by this and then the image being in there. So you're going to actually land in W minus 1. So now, and then, okay, so, you get a map from X1 this to X1 this, but in fact, by weight considerations, you can see that actually this map is going to be injected. So this X group, you can think about it as a subgroup of this X group. Now, EP is an element there, so you can push it for, you can think about it as an element there. Now, all of these, various EPs live in the same space, so you can add the map there, and I'm going to denote that sum by just the script EM and call it the total class of M. Now, Deligne's theorems describes UM in terms of this total class of M. Namely, here's the result. It says that, so remember, this guy is an extension of 1 by W minus 1, and inside this you have the object UM. Yeah? Now, what the theorem says is that U of UM is the smallest sub-object of W minus 1 and M, such that EM is the push forward of an extension of 1 by UM. So such that EM is in the image of the push forward map under inclusion, inclusion of this guy into this, of this X group going to that. So it's the smallest, UM is the smallest sub-object of this guy, such that the EM pushes forward from an extension of 1 by UM. And one word about this proof, unfortunately, I don't have more time to talk more about this, but I do want to make the remark that this proof actually, to show that EM is the image of, that is the push forward of an extension here, Deligne actually constructs that extension. So the proof, that part of it is very concrete, explicit, in that he actually constructs an extension of 1 by UM, which pushes forward to EM. He uses the weight filtration to do this. Now, okay, so now the next part, so from this point on is a summary of our joint work with Kumar. See, the point is that, so we start, from the following question. See, the sum of these EPs, now you know that comes from UM by Deligne. Now, the natural question to ask is if each EP just individually also comes from UM. So there's some, of course, it does, but what about each of them individually? And the answer is that not in general. And you can construct a counterexample using, counterexample with one motifs using Jacquinot Ribet's results on deficient points on one motifs from the 80s. So in general, it's not true that every every extension class is going to come from U. But now, so the theorem that I'm going to state is that is going to give us a scenario where actually EP does come from U. So let's start with introducing some notation here. So maybe let's look at the picture instead of the writing. See, okay, so this is Z2, but the way I'm writing Z2 is similar to the way you label entries of a matrix. Okay? And so this is the diagonal, I equals J. And then this is, okay, so this is J being P, this is I being P, and so this is P comma P. And then this set is the purple set. So from here and above, so this is square, infinite square. And then the J2 is the green portions. So it's above the diagonal minus the purple portion. And then we're going to say that M, or in fact, associated graded of M if you want, because the condition only depends on the associated graded of M. We're going to say that this satisfies the first independence axiom. So this I is for independence. The first independent axiom for P if you look at the direct sum of internal harms ger J ger I, where the pair I comma J runs through the points in this set, and direct sum of the same things, but as now I comma J runs over indices in the green sets. We're going to say M satisfies the independent axiom 1 for P if these two objects don't have any non-zero isomorphic sub-objects. So in a way, they're very independent from each other. And a sort of an example where this will hold is where, if you want these two objects not to have any non-zero isomorphic objects, one way to guarantee that is to make sure that they actually don't have any common weights at all. So that's the example. This holds if the two objects don't have any common weights. So, the set of weights of these two things, which is, I minus J, as the pair runs through J1, and these two guys are non-zero, and then, J2, these two sets of weights are disjoint. And, examples we're going to give actually, the condition will hold for weight reasons like this. Now, our first theorem with Kumar is the following. So the statement is, to us is very, is rather strange. And I am going to hopefully, there will be a little bit of time to talk about the proof, see where the conditions come from, but still it's very mysterious. So suppose the following hold. So suppose associated grade of M is semi-simple. So that's a very mild condition if you're thinking about geometry. It will hold if you're thinking about geometry. And then 2, suppose M satisfies the first independent axiom for P. Okay? Then actually EP, this extension class, the Pth extension class, will come from UM. So somehow, and I'll talk about the proof, but the proof, you'll see where this is being used, but I don't think it's sort of like I think it has to be like some sort of like more, at least in the case of motives, some geometric reason, some geometric interpretation for why this is happening. But so if M satisfies the first independent axiom, then EP will actually come from U. So the corollary of this is the following. Suppose that M actually satisfies what I'm going to call the second independent axiom. So there's no P here. This is saying that actually, if you look at this whole, up above the diagonal, all the weights you have are distinct. This is what this independent axiom is saying. So suppose that the numbers I minus J where I is less than j, so you're above the diagonal, and so ger I of m, ger j of m both non-zero. Suppose these are all distinct. So in other words, if you look at w minus 1 and m, this guy actually has, okay, so if the number of weights of m is n, this guy has n choose 2 distinct weights. Okay? Then, well, then this axiom will actually hold for all p. For all p, and then in fact, without, right, so, and yeah, and also assume that ger m is semi-simple. Sorry, I didn't write this there, but then every EP will come from U. So for example, suppose you're in a situation where the weights of M are like this. Then, all the differences you get between these numbers are actually distinct. And that, if you have a motive with these weights, then each of its extension in P will come from U. It's U.
Payman, I might, it's interesting. This is, as you point out, it's kind of mysterious. But one is reminded of, in pure Hodge structures, there's a level, which is sort of the gaps of the P and the Qs. And sometimes when the level is low, you can say something about the Hodge structure or the Mumford-Tate group, but you can't say in general. This seems to be playing that kind of game, but on the weights.
That's interesting.
Which is a different, which is quite different.
Yeah, it's. I mean, as I say, it is very strange. Yeah. But so let's look at, before we. This was for my own, for myself. How long that's supposed to take? The next section. So the plan for so this is sort of like the one of the main results here. And then what I'm going to do the rest of the talk is that first I'm going to give an application of this to motives. And then after that, hopefully there'll be time, we're going to come back and talk about the proof of this result. But application to motives. Okay. So for now, you're not going to assume that, we're in the category of motives, but assume that associated graded of M is semi-simple, which will be the case if you are dealing with it. Now, recall that UM is a sub-object of W minus 1 and M. And then, so here's the definition. We're going to say that UM is large if it's actually equal to W minus 1 and M. So it's equal to the largest thing that it can be. So there's no sort of, there's no, if you want to call it defect or deficiency or anything, things like that. So it's actually, it's equal to the largest thing it can be. And then here's an application of the previous result. Suppose, okay, so suppose P is is less than 0, and suppose you have an object M. Remember, we are assuming that the associated graded is semi-simple. Suppose that you have an object M whose highest weights are P and 0. So those are its two highest weights. Okay? And then so its ger 0 is just a unit object. So that's the same thing as saying that M mod WP is actually just a unit object, and then ger P is non-zero. So okay, yeah. So when you look at essentially when you look at the associated graded looks like this. There's a ger P, which is non-zero, and then there's a 1, and then there's like lower weight stuff. This is how the associated graded looks like. Suppose, moreover, that U of WP is large. So again, maybe I should write it like this. So, when you look at M, there's WP, and then after that, it's W, 0, which is M itself, but, there's no jump after this point. And what you're saying is that suppose, so WP has a large U, and so maybe, I don't know if these like, sort of like kind of diagrams are more misleading or helpful, but so basically up to here, you're assuming that it's large. And then suppose that M mod WP minus 1 also has a large U. So here you have, WP minus 1. There is actually a jump there because you assume that curl P is non-zero. And then what we're saying is that, if I just look at this portion, by which I mean, take these guys and mod them out by this, the object you get, so M mod this also has a large U. Yeah? Suppose these two things hold. And then, moreover, suppose that M satisfies the first independent axiom for P. So that's the axiom that says that, those two objects here, these two guys don't have any non-zero isomorphic sub-objects. Now, where was it? Yeah. Then U of M will also be large. So, up to this guy having a large U, and then just this portion having the large U, by which I mean this quotient having a large U, and then suppose moreover that the first independent axiom holds for P, then UM is going to be large as well. And again, you're tempted to think that, look, I mean, maybe this is not necessary, look something unnatural there, but it's actually important because we can construct counterexamples, again, with one motives, again, the efficient points on one motives that, satisfy these two conditions. They don't satisfy this, and then the U is not going to be large. So, something is happening there. Somehow this thing actually is important. So, okay, so now, this kind of, the way, one way to think about this is that, okay, so both of these guys are sort of like simpler motives, simpler objects, and then somehow from, these two simpler ones having large U's, you can deduce that M itself also has a large U if you have this independent axiom. So here's a question, suppose you give me this guy and this guy. So, the motivation for this question is the following. Suppose you give me two simpler motives, this guy and this guy with large U's, simpler objects with this guy with large U's, and somehow I want to patch them together to construct an M, or to show that an M exists, which also has a large, and then if this condition holds, UM will be also large. Now, okay, so the question is the following. So suppose, okay, P is again less than 0, and suppose, okay, so given L, so this L is going to be, what you want it to be, this WpM. Suppose L, it has weight at most P, and then its GER P is not equal to 0. So its highest weight is actually equal to P. And then you're given an object N, which is, well, the N is going to, and you want it to be this guy here. It's an extension of 1 by GER P of L. Suppose these two guys are given. And then is there an M with the property that its WP of M is isomorphic to L, and M mod WP minus 1 of M is isomorphic to L? So as I said, so the motivation for this question is that somehow from smaller motives, you're hoping to construct more sophisticated motives which still have large unipotent radicals. And in fact, before I get to the answer to this, maybe I should have also said that the reason that this is interesting in the first place is, again, because of the period conjecture. If UM is as large as possible, that means that, the periods, supposedly, conjecturally, should have the highest possible transcendence degree. Okay, so now the answer to this question, when you can patch together an L and an N, see, this is actually a question that, it actually shows up in SGA 7. So Gordon Lake has this discussion of what he calls extension panache. And so the answer is the following. So, you look at, consider this extension defined by L. So, P minus 1 into L, and then associated weighted, and then apply the functor harm 1 comma blank to this, you get a long exact sequence. I've written a part of it here, x1 to this, to x1 this, x1 this, and then x2 this. And then, from the, if you look in the construction of this long exact sequence, which is due to, originally due to Yoneda, this connecting homomorphism is actually the concatenation with, so if I call this L, it's just concatenation with L. So if I have two extensions, you can concatenate them and get a two extension. And this connecting homomorphism is just concatenation or composition. And then n, well, n is an extension of 1 by GER-P. So, it gives you an extension, the extension, I'm going to call that with the script n. And then, so you want an object M such that, its extension pushes forward to n. Under this, well, by exactness of this, that will happen if and only if LON is 0. So the obstruction to being able to do this is an element in X2. So M exists if and only if this element of X2 is 0. Now, in the category of, now, thinking about motives, in categories of motives over number fields, conjecturally, X2 groups should just vanish, higher X groups. So higher X2 and higher X groups should all vanish for motives over number fields. So, then you can do this, well, this conjecturally, but in some cases, it's no longer a conjecture. So suppose, here's the first example. Let's take our T to be the category of mixed Tate motives over Q. And I'm gonna work, think about Blavatsky's mixed Tate motives over Q. So this now is a Tanakian category over Q, and it has the right X groups. But all you need here is that, it doesn't have to be really Blavatsky's construction as long as the X groups are the correct X groups. They are the correct X groups. So let's recall what the X groups are. The X groups, so extensions of 1 by Qn are as follows. If your n is 1, this is going to, so the extensions are going to be given by Kumar motives, and this is Q. This is so Q star tensor Q. If n is odd and odd bigger than or equal to 3, this is a one-dimensional space. And in fact, so if you take a generator of that, any non-zero element there, it's you can call it the motive of Z of n if you want. Period is going to be Z of n. So an example, we're going to look at that. And then otherwise, this X group is going to be 0. So if n is less than 0, or less than or equal to 0, or more interestingly, if it's an even positive integer, the X group is going to be 0, which reflects the fact that when you look at periods of even values of the zeta function, there are powers of pi. Even powers of pi. So those are X1 groups, and then higher X groups all vanish. So in particular, X2 groups all vanish then. So these are theorems now. These are not conjectures. So now, let's continue with our example. So what we do is that, okay, so I'm going to take an odd positive integer n greater than or equal to 3. Let's just take 3 itself. So I take a non-zero element of the corresponding X group, and the object you get, let's call it L3, but for simplicity, let's call it L. It's a non-trivial extension of 1 by Q3. Motive, the zeta of 3 is going to be a period of this. So the construction of these things goes back to Deligne in his paper on the fundamental group of P1 minus 3 points. Now, okay, so that's the L that we're going to be, well, that's, so yeah, the L that we're going to work with is going to be a twist of that, but so L is, for now, it's the motive of Z of 3, period is Z of 3, extension of 1 by Q3. And then I'm going to take N to be this Kumar motive. So this is a 1 motive given by Z to GM and sends 1 to 2. Again, nothing is special about 2. You could take anything other than 1 and minus 1 here. As long as it takes something non-torsion, the rest what we're going to say is valid. So now this is a non-trivial extension of 1 by Q1, this Kumar motive. And then, okay, so now, so this is 1 by Q1, and then you want to be able to do what we talked about before. You want an extension of Q1 by something. So I'm going to shift this guy by Q1. So now I'm going to look at L twisted by Q1, L1. So that's an extension of Q1 by Q4, and it's a non-trivial extension because L was a non-trivial extension. And then because X2 groups all vanish in the category of mixed Tate motives, you can patch these two guys together. So there's a mixed Tate motive over QM obtained from these two guys. It's associated graded as Q4 plus Q1 plus 1. and it's W minus 2, so up to this portion is motive of zeta 3, shifted, twisted by 1. And then when you mod out M by well, W minus 3, but that's the same as W minus 8. That's why I wrote W minus 8. So when you mod M by, well, up to this portion, then you get N. So there's a motive like that. And in fact, this is a canonic, up to isomorphism, this is unique. The reason being that when you look at this long exact sequence here in this example, here you'll be looking at X1, Q4, which is 0. So that's why the object that you're going to get is actually going to be unique. So there's this canonical object with these properties. And now by the previous results, because look, so see, look at the weights of this thing. The weights of this are 0, minus 2, 0, minus 2, and minus 8. And actually, the independent axiom, the sort of strongest independent axiom holds. The 3 numbers you get from the, from pairwise differences are actually all different. So now this guy itself, both of these guys, because both of these guys will have large U's, because so this is easy to see because they only have 2 weights and they are non-split extensions, total non-split extensions. Both of these guys will have large U's, and then your independence axiom also holds. So it follows from the result that actually M has a large U. But now why is this interesting? See, let's think about the periods. So first of all, okay, we think about sort of the period conjecture. So one side of that is the motivic Galois group. Now we know what the motivic Galois group is essentially here. See, okay, so it's the motivic Galois group. Remember, it's the unipotent radical. It's the algebra. It's this, and then modded out by that, you get the motivic Galois group of the associated graded. In this case, that's the same as motivic Galois group of Q1. Okay, this is now GM. This is one-dimensional. This dimension is 1. And then this guy here, because by being large, this guy is actually all of W minus 1 and M. So it's going to be a 3-dimensional thing. W minus 1 and M here, it's 3-dimensional. So this guy, this motivic Galois group is 4-dimensional. So period conjecture predicts that actually, the transcendence degree of the field generated by the periods has to be also 4. But now let's think about what the periods are. See, coming from motive of zeta 3, and then twist of it, the numbers you're going to get are, so the field will include zeta of 3, the 2 pi I. It also includes log 2 that comes from the Kumar motive. But it's supposed to be actually, it's supposed to have transcendence degree 4. So M should have what I'm referring to here as like a new period. So M should have some period that, supposedly, according to the period conjecture, shouldn't be generated by these guys. And then, what is that? We actually don't know. So this is a really interesting question. So one thing to keep in mind is that, is that M is not actually a mixed state motive over Z, and that's because of, the Kumar motive. I mean, if it was a mixed state motive over Z, then you say that, okay, it has to be generated by multiple zeta value, but it's not actually a mixed state motive over Z. Now, building on this example, so maybe I'm running out of time, so I'm going to do this very, very quickly. So you can construct, motives with higher weights too. Build on the previous example. You could sort of, twist the weights, and again, take maybe a motive of a zeta value. This time, what I'm doing here is actually I'm taking the motive of zeta 5. So I start with the original motive. I twist it so that now you have something of these weights. And then I'm going to try to patch that together with the motive of zeta 5, which is an extension of 1 by Q5. And you can do this because X2 groups vanish. So then you're going to get these, you get something it's called M prime. Again, because of, the independence axiom holds, the weights are, the numbers, the pairwise differences are now all distinct. That's why, if you try to twist this with something less than 5, that would not work. But if you twist it by 5, then the differences will be different. Your independence axiom holds. and then you're going to get something large. And then if you think about the periods of this, you'll see that now the periods are, they also include zeta 5. And then period of the M, the earlier M, that's 5 numbers. But then, if you look at the dimension of the motivic Galois group, that's actually 7. So, this M prime should have 2 other new periods, which again, we don't know what they are or like what sort of numbers they should be. So I think maybe 5 more minutes. I'm just gonna give some indications on the proof of theorem 1, and I have actually quite a bit to say here, but there's not enough time. So let me see sort of a.
You still have 13 minutes.
Oh, we can go. I can go until 1 o'clock.
Yeah, sure.
Oh, okay.
I mean, so, people have questions, they can interrupt now.
Okay. Okay, so then maybe there'll be time to do this. Okay, so it's natural to expect. See, the point is that EP, if you remember its definition, that was, so you start with the extension of WP into M, WpM into M, and then M mod WP 0. And then you wrote that as an extension of 1 by this guy here. And then you pushed it forward to W minus 1, but originally it was just an extension of 1 by this. So it's natural, so U is related to the total class. So it's natural to expect that EP, the pth extension class, should be related to actually just, well, the intersection of U with this sub-object of W minus 1. I'm going to call this W, call this UP. And this is indeed the case. So it's easy to prove that if you write your EP, okay, so it's an extension of 1 by this harm, okay, let's call subject in the middle, let's call that the object in the middle, let's call that M prime. You can explicitly write it, but let's just call it M prime for now. And then it's easy to see that UP is because UP as an extension, as a sub-object of this. It's easy to see that UP is actually the smallest sub-object of this, such that M prime modded out by UP belongs to the subcategory generated by WpM and M mod WpM. And the proof of this is quite simple. So, and it's going to give us some ideas about how the proof of the result, the sort of more important result goes as well. So let's quickly go over this. See, if you take omega of this UP, okay, so that's going to be now omega of this intersect omega of this. And then, well, this is now the Lie algebra of the U group with respect to omega. And then, well, the part of it that actually, so an intersection with this, if you think about it, you'll see that actually that's the same as this, to say that this is the Lie algebra of the kernel of the restriction map that you have from the group of M to the group of WP plus M mod WP. So the algebra of the elements that act trivially on both WP and M mod WP. And then, so if you call this extension, let's say capital UP, then see this, you're trying to show that some object belongs to the subcategory. And now in view of Tanaka formalism, that's to say, and so you want some representation of this group to actually belong to be a representation of this guy, factored through a representation of this. So that's to say that you want so to be in this subcategory is the same as to actually have a trivial action of this guy. And that's now an explicit calculation. You can directly check that if you take any object A, any sub-object A of this guy, then UP is going to act trivially on its omega of M prime mod that by omega A, if and only if UP is contained in A. But again, as I said, this is equivalent to saying that M prime mod A belongs to the subcategory generated by this. And well, that's the same as this. So that gives the result. Now, idea of the proof of, the first theorem that we had that, gave a sufficient condition for actually EP coming from U is the following. See, one thing I want to say about before we proceed is that if you think about Deligne's proof, as I pointed out, that's a very different type of proof, because to show that the extension comes from pushes forward from U, he actually constructs an explicit extension of 1 by U, which pushes forward to E. But our arguments are arguments along this line, more sophisticated versions of this. So, you're not going to get actually it's a different type of argument. You're going to look at the quotient, the quotients, and try to say something about that quotient. Okay, so now idea of the proof of theorem 1. See, the point is that what you want to do, back to this proposition, what you want to do is that you want to essentially refine this result so that you replace this category by some smaller categories. And why do I say that? See, suppose you could replace this guy by just the category generated by WpM. Okay, this is definitely contained in here because, well, up to P part of it is here, and then after that it's contained in there. So this is contained. This is a smaller category, and suppose that you could replace this category just by that, and you're assuming that that's a semi-simple category. Then what you would get is that actually, well, this object modded out by UP belongs to a semi-simple category. So in particular, the extension would split, and that would give you what you want. This would be 0, and then the extension is push forward 0, and then so on. So that's why you want to replace this by smaller things. But the way this result is formulated, that actually is hopeless because the point is that when you mod this out by UP, this modded out by UP itself doesn't have to be a semi-simple object. So there's no way to hope that actually M prime modded out by UP should be something semi-simple necessarily. So you will need a reformulation of this result such that now this can be made smaller. So that's the second thing here. You need a more natural formulation of that proposition. So now in this formulation, it goes as follows. So first, let's start with the definition. So suppose you have an object A of T and an extension of 1 by A, E. You're going to say E originates from a Fulton-Akin subcategory S if E is the push forward of an extension in S actually. So to be more precise, if there's some object A prime of S, map a morphism from A prime to A, such that if you look at the push forward along F from this X group to this X group, this is extensions in S, E belongs to the image of this. Then you would say that E originates from the subcategory. And now the new formulation of proposition 3 becomes that UP is the smallest subobject of this, such that this extension, and by this I mean the push forward of EP under the quotient map, this extension originates from this subcategory. And now with this formulation, well, there's two nice things. One, that this extension here, you can actually think about it two different ways, and the statements will be equivalent to each other. If you think about an extension of 1 by harm modded out by UP, or W minus 1 modded out by UP. The other nice thing is that, even if you could, and in fact we can now replace this guy by a semi-simple category, all that means is that this extension splits, but it doesn't mean that, the object in the middle has to be a semi-simple object. So it's a very natural, much more natural formulation of that. Now back to proposition 3. Okay, so now proposition 3 can be refined, and then the theorem that they prove is actually the following. See, remember these two sets we had, they were like the green one, but like all of this portion, and then the purple one. And then I'm going to take a Q less than or equal to P, and I'm going to truncate that set. So I'm going to start actually from here. So now these green ones are J2PQ, and the purple one is J1PQ, which is the same as what we had before. And the theorem is the same, is the following. This is the result that we actually prove. Suppose one of the following holds. Either GER-M is semi-simple and the two objects similar to before, but only you look at this region and this region now. These two objects don't have any non-zero isomorphic subobjects. Or the two objects above, the same objects actually have distinct weights, completely distinct, have disjoint weights. Then this extension originates from this subcategory. And now, well, first of all, notice that this is smaller than the previous subcategory because this is what you had in the proposition. And now, well, this is definitely contained in there. And then here you only have WQ, which is, well, Q is less than or equal to P. So, that guy is contained in here. And then the mixed stuff there may not appear there at all. So that's the first observation. And then, how do you get the theorem, the first theorem that we stated from here? The point is that if the independent axiom 1 holds, then you actually have this for all Q. So you can, you can get rid of this by taking your Q small enough, and then you assume that this is semi-simple. So this will be a semi-simple category, and then this will be 0. Now, indications on the proof, I've got 3 minutes and just enough time to actually tell you why those conditions matter, where they are used. Okay, so there's 3 items here. The first item is sort of is the following. See, this category here that is of interest. So, you look at the, the restriction map from the category, from group of M to the group of these 2 guys, the sum of these 2 guys. The kernel of that, let's call it this guy. And now it's easy to see that, to say an extension originates from this subcategory, again, is a statement about, kind of like triviality of the action of this. But more precisely, this time it's about right exactness of U greater than or equal to Q invariance applied to the sequence. So that sort of like gives a bridge that you wanted to show that the extension originates from here. This is really what you need to check. You need to show that some U greater than or equal to Q invariant elements. Now, the algebra of this guy, again, naturally becomes there's the sub object associated with that. I'm going to denote that by U underline greater than or equal to Q. It's the intersection of U and this harm here. All you want here is that the action on just WQ is 0. Now, the trick is that, okay, so you want to work with some fiber functor omega. The trick is that, you take omega to be a graded fiber functor. And it's going to make the calculation much easier. And you're going to, so in other words, you start with some arbitrary fiber functor, but you don't work with that. You compose it with the associated graded fiber functor, and then you work with this fiber functor instead. And now, where do those conditions, matter? See, okay, so these 2 conditions of the statement of the theorem. So these are about the independence axiom. These imply that the associated graded of this U object decomposes as a part corresponding to the green region and a part and a sub-object corresponding to the purple one. That's what those axioms guarantee. That this decomposes as a sub-object contained in here in this direct sum, where you're in the green one and then in the purple region. And then that will tell you that, well, once this decomposes, note that I'm working with the associated graded here, but once that decomposes, well, so does its omega naught, right? But then that's to say that actually omega of U itself decomposes. And so it decomposes accordingly. And that's essentially, that's the only place these conditions hold. So once you have this decomposition, what that means is that if I have an element of U of that, that the algebra, that lives there, then actually that guy becomes a sum of something in the green one and something in the purple one. And that's the key thing here that is used in this proof. Okay, so it's 1 o'clock, so kind of perfect timing, but I also kind of I don't know, I was like I had to sprint towards the end, but yeah, that's it.